Okay, so in this video, we're going to look at how to calculate the area of one petal of the graph of a polar graph. So in this particular graph, we're going to look at is this one. So this is one we used as a previous example for finding derivatives, but we have this nice graph, and we'd like to find out what the area of one petal is. Now, if we know what the area of one petal is, we can multiply it by 4 to get the value for the entire area enclosed by the function. But instead, we're just going to work on one petal at a time, and then symmetry will take over if we need more. Now, considering this graph, the petal is going to begin and end when it crosses the origin. So to start with, we're going to have to find values of theta that are going to actually cross over that origin. So we're going to set r equal to 0, and we're going to solve for theta equals 0. So the 2 doesn't do anything. And so we're going to look at values of 2 theta, where cosine is equal to 0. Cosine of theta is equal to 0. Cosine of theta is going to be equal to 0 for pi over 2 and negative pi over 2, etc. Odd multiples of pi over 2. But this is 2 theta, and so we actually want theta then will be negative pi over 4 and positive pi over 4. Again, that is consistent with our graph. We're going to get pi over 4 is going to be here. Negative pi over 4 is going to be here. So this makes sense. And these two values will bound this particular petal. Now, if you're dealing with something like a sine function, then you'll have a similar procedure, but your petals will be sort of in the middle of the quadrants instead of on the axes, around the axes. And so you will have to choose 2 consecutive values for theta that are going to surround one petal. So for instance, it might be 0 and pi over 2 instead of negative pi over 4 and pi over 4. Just kind of keep that in mind. It's not just any 2 consecutive values. It has to be 2 values that consecutively surround a single petal. So if you're going around this curve, you can come out here at negative pi over 4, you go around the curve, and then you close out that petal at positive pi over 4. So this is, if you integrate between these, that's one consecutive string of values. If you were to start with pi over 4, then you would actually end up going this way, and you would end up with a petal that's actually in a slightly different place. So again, you just want to be careful about how you select them. You don't want to get negative values or weird outcomes. All right, so we have chosen our 2 thetas. Now the area formula for calculating in polar coordinates is going to be 1/2 the integral from A to B, our 2 angles, or we can say alpha and beta since they're angles. Greek letters are often used for our angles, of r of theta squared d theta. Now this formula may seem a little odd, but after you take multivariable calculus, it will be entirely clear as to why this formula in one variable has to be this way. But for right now, I'm just going to leave it. That is the formula we need to use. And so we'll have our 1/2, and then our limits of integration will be negative pi over 4 to pi over 4. And then we're going to square our 2 cosine 2 theta. So that'll be 4 cosine squared of 2 theta. Square the function, not the angle, d theta. Now, we can also use symmetry to save us a little bit of additional arithmetic here. And that is if you look at this petal, it is exactly split in half by the x equals 0 line, the x-axis, theta equals 0 line. So we could actually just calculate the area of half the petal and then double the result. And so that's what I'm going to do just to make myself a little bit less arithmetic, as I said. So the 1/2 will get canceled by doubling the result. And then we'll start at 0 and we'll just go to pi over 2 of this same expression. And then this will cancel to 1 and I can pull the 4 outside as needed. This should be pi over 4. So again, just applying symmetry. Now, this is a squared cosine, and so I need to use my power reducing identity in order to actually be able to integrate this. This is going to be equal to 1/2 1 plus cosine 2 theta. Now, I already have a 2 theta, so this is telling me I need to double my angle. So when I recreate this over here and replace my cosine squared of 2 theta with this expression, I'm going to have to double my angle again. So it was 2 theta. And now it's going to be 4 theta. So doubling that angle. The 1/2 and the 4 can simplify a little bit. And so that's going to leave me with 2. And then my integral from 0 to pi over 4 of this. But now it's in the form that I can actually do the integration. And so I'm going to end up with 1 becomes theta, and then cosine will become 1/4 sine 4 theta, evaluated from 0 to pi over 4. And so when I plug that in, I'm going to get pi over 4. And then if I plug in pi over 4 into sine of 4 theta, that's going to be sine pi, which is 0. And then when I plug in 0, I'm also going to get 0 and 0. And so I'm going to end up with pi over 2 as the area of one petal.